Imagine a platinum planet floating in space, holding more platinum than all the platinum on Earth combined, valued at an astounding $7 quadrillion. This isn't science fiction. This is space mining, and it's getting closer than you think. Right now, private companies and space agencies are setting their sights on these cosmic treasures above our heads. But to dig up these space gold mines, simply flying there isn't enough. The challenges are immense. Today, we're going to explore the grand adventure of space mining, from the incredible riches hidden within the asteroid belt to the black technologies that could fundamentally transform humanity's future. When we talk about space mining, we're not just referring to any celestial body. The primary targets for resource extraction are overwhelmingly asteroids. These rocky remnants from the early formation of our solar system, especially those located within the asteroid belt between Mars and Jupiter, are true gold mines, or more accurately, platinum, iron, and nickel mines. To understand why asteroids are so valuable, we need to look back at the birth of our solar system, around 4.6 billion years ago. A massive cloud of gas and dust began to collapse under its own gravity, forming our sun and planets. During this process, various elements condensed at different temperatures. Heavier metallic elements tended to sink to the cores of the forming planets, while lighter elements formed their crusts and atmospheres. However, in the asteroid belt region, Jupiter's immense gravity prevented most of the material from coalescing into a single giant planet. Instead, it remained in the form of countless smaller bodies, asteroids. Many asteroids are thought to be the strip cores of ancient protoplanets that never fully formed or were shattered in collisions. This means they could be rich in metals that are largely inaccessible deep within Earth's mantle. Not all asteroids are created equal in terms of resource potential. Scientists classify asteroids into several main types based on their composition, which gives us clues about the treasures they might hold. C-type, carbonaceous asteroids. These are the most common type, making up over 75% of known asteroids. They are dark in color, rich in carbon, and also contain significant amounts of water and organic compounds. While not as rich in precious metals as other types, their water content is incredibly valuable for space exploration. Water can be broken down into hydrogen and oxygen, which are essential for breathing, drinking, and most critically, rocket fuel. Imagine refueling spacecraft in orbit using water harvested from an asteroid. This would drastically reduce the cost and complexity of long-duration missions. Some C-type asteroids are estimated to contain trillions of liters of water. S-type, stony asteroids. These asteroids are primarily composed of silicate materials and nickel iron. They are brighter than C-type asteroids and account for about 17% of the total. S-type asteroids are considered prime targets for metallic resources, particularly nickel, iron, and smaller amounts of platinum group elements, PGEs. M-type, metallic asteroids. These are the rarest but most appealing targets for mining. As their name suggests, they are believed to be composed primarily of nickel iron and are often rich in gold, platinum, iridium, and palladium. They are thought to be the exposed cores of shattered protoplanets. The platinum planet we mentioned earlier, 16 Psyche, is the most famous example of an M-type asteroid. It's estimated to be over 90% metal in composition, with a potential value that is almost incomprehensible, far exceeding the global economy. While the main asteroid belt holds the lion's share of the solar system's asteroid wealth, space mining companies are currently focusing on near-Earth asteroids, NEAs, as the name implies. NEAs have orbits that bring them relatively close to Earth, making them easier to reach with robotic missions. Tens of thousands of NEAs have been discovered, and a significant portion of them are C, S, or M-type. Reaching NEAs requires less time and energy, making them the most economically viable targets for initial mining operations. However, their smaller size means they contain less total material than main belt asteroids, but their sheer numbers provide ample opportunities. The challenge lies in accurately assaying their composition from such a great distance. 4. Why space mining? Extracting resources from space might sound like a futuristic luxury, but it's increasingly becoming a necessity for Earth. As the global population grows and the demand for raw materials escalates, Earth's finite resources are under immense pressure. Resource depletion and environmental impact. Our modern technological society relies heavily on various metals and minerals. From the rare earth elements in our smartphones to the copper in our wiring and the platinum in car catalytic converters, in many cases, demand continues to outstrip supply. Terrestrial mining is an energy-intensive and environmentally destructive process. It leads to deforestation, habitat destruction, water pollution, and significant carbon emissions. Beyond supplementing Earth's dwindling resources, space mining is also seen as crucial for the expansion of human civilization beyond our planet. When we envision lunar bases, Martian settlements, and orbital habitats, the ability to live off the land becomes paramount. Transporting every piece of equipment, every drop of water, and every kilogram of building material from Earth is incredibly expensive and inefficient. The cost to launch 1 kilogram of payload to low Earth orbit can range from thousands to tens of thousands of dollars. Imagine the astronomical cost of launching all the materials to build a Martian colony from Earth. This is where the concept of in situ resource utilization, ISRU, becomes vital. ISRU refers to the practice of acquiring and using resources found or manufactured at the exploration site. For example, water from asteroids and lunar poles. Water can be broken down into hydrogen and oxygen, which are essential for breathable air, drinking water, and most importantly, rocket propellant, liquid hydrogen and liquid oxygen. This fuel depot in space would dramatically reduce the cost and expand the range of deep space missions. A spacecraft launched from Earth with a full fuel load might only be able to reach certain destinations, but one able to refuel in orbit with asteroid water could go much further and carry more payload. Metals for construction, iron, nickel, and other metals from asteroids could be used for 3D printing components for spacecraft, satellites, or even entire orbital structures. This would reduce the need to launch large, complex structures from Earth, making the development of space infrastructure more efficient and economical. Imagine printing a new satellite component in orbit instead of waiting for one to be launched from Earth. Regolith for shielding and construction. Lunar regolith, moon dust, and asteroid material can be used as shielding for habitats against harmful solar and cosmic radiation, and potentially as building material through techniques like sintering or additive manufacturing. ISRU isn't just about saving money. It's about enabling a sustainable, self-sufficient presence in space. Without it, humanity's expansion into the cosmos will continue to be constrained by Earth's immense gravity. The dream of space mining is no longer confined to space agencies. A new breed of private companies, fueled by venture capital and an entrepreneurial spirit, are leading the charge, developing innovative technologies and strategies to make this vision a reality. While some early attempts face challenges, renewed interest and technological advancements are creating a more robust ecosystem. Pioneering ventures and new players, early pioneers, such as Planetary Resources and Deep Space Industries, emerged in the early 2010s, capturing the public imagination with their ambitious asteroid mining plans. Although both companies eventually faced financial difficulties and were acquired, they laid crucial groundwork for subsequent developments, proving the technical feasibility and drawing significant talent into the field. Their efforts helped de-risk the industry and demonstrate that it wasn't just a pipe dream. Today, new players are building on this legacy, often with more focused strategies or novel technological approaches. Some notable examples include AstroForge. This California-based startup is working on refining platinum group metals in space, thus reducing the need to transport raw ore back to Earth. Their approach involves using proprietary thermal vacuum technology to extract and purify metals directly from asteroid material in orbit. They successfully launched a test payload in early 2023, demonstrating the first steps of their in-space refining process. Their goal is to prove the economic viability of space mining through small-scale, high-value extraction. Carmen Plus, hypothetical, but representative of an emerging trend. This company focuses on developing modular, autonomous robotic miners that can be deployed to multiple asteroid targets. Their vision is to create a fleet of small, specialized robots capable of performing exploration, extraction, and initial processing with minimal human oversight, significantly reducing operational costs and risks. TransAstra. This company is developing solar thermal propulsion technology and inflatable space habitats, which are crucial for transporting large quantities of material from asteroids and establishing long-term human presence in deep space. Their API spacecraft concept aims to capture asteroids into inflatable bags for transport and processing. Lunar Outpost. While primarily focused on lunar exploration and resource utilization, companies like Lunar Outpost are developing technologies for lunar regolith mining and processing, which share many similarities with asteroid mining techniques. Their expertise in extraterrestrial robotics and resource handling will be directly applicable to asteroid missions. These companies aren't just building rockets. They are developing sophisticated robotic systems, advanced materials science techniques, and novel propulsion systems. They are proving that the pursuit of space resources is a multifaceted challenge, requiring innovation across various engineering and scientific disciplines. It's not just private enterprises. Space agencies and national governments are also increasingly recognizing the strategic importance of space resources. NASA's Psyche mission, while not a mining mission, NASA's Psyche mission, launched in 2023 and currently en route to asteroid 16 Psyche, is a crucial step in understanding M-type asteroids. The data collected by this mission will provide invaluable insights into the composition, structure, and formation of metallic asteroids, directly informing future mining strategies. Understanding the geology of these bodies is the first step towards effective resource extraction. Artemis program. NASA's Artemis program, aiming to return humans to the Moon and establish a sustainable lunar presence, heavily relies on ISRU, The experience gained from extracting water ice from the lunar poles and processing lunar regolith will provide invaluable lessons and technologies for asteroid mining. The Moon can serve as a testbed and stepping stone for deeper space resource utilization. The 1967 Outer Space Treaty declares space as the province of all mankind and prohibits any nation from asserting national appropriation over celestial bodies. However, it does not explicitly state who owns resources extracted from space. Luxembourg has taken a leading role in this regard, enacting legislation that permits private companies to mine and own space resources. The United States has also passed similar legislation. Developing international norms and laws for space resource utilization is an ongoing, complex, and vital discussion. The grand challenges of space mining. Despite the alluring potential, space mining is arguably one of the most challenging endeavors humanity has ever conceived. The obstacles are immense, spanning engineering, economics, and ethics. Space is vast, cold, and unforgiving. Even the closest asteroids are millions of kilometers away. Travel time. Reaching an asteroid takes time, months to years depending on the target and propulsion system. This means long mission durations, requiring highly reliable spacecraft and autonomous systems. If something breaks millions of miles away, you can't easily send a repair crew. Orbital mechanics. Asteroids are not stationary targets. They are constantly moving at incredible speeds. Intercepting and rendezvousing with an asteroid requires precise calculations and sophisticated navigation. Capturing or manipulating an asteroid's trajectory is an immense engineering feat. Energy requirements. Reaching an asteroid and returning valuable material requires immense energy. While advanced propulsion systems like solar electric propulsion, ion thrusters, and even nuclear propulsion are being developed, they are still highly complex and expensive. Delta V, change in velocity, is key for these missions, and the requirements are huge. Space is a vacuum, accompanied by extreme temperature fluctuations, harsh radiation, and no atmosphere to protect equipment or personnel. Vacuum. The absence of air means traditional machinery designed for Earth would fail. Lubricants evaporate, and heat dissipation is challenging. All systems must be designed to operate in a hard vacuum. Extreme temperatures. Asteroids experience dramatic temperature swings between their sunlit and shadowed sides, from hundreds of degrees Celsius to near absolute zero. Mining equipment must be able to withstand these extremes without degradation. Radiation. Beyond Earth's protective atmosphere and magnetic field, spacecraft and astronauts are exposed to relentless solar radiation and cosmic rays, which can damage electronics and pose severe health risks. Robust shielding is critical. Microgravity. The extremely low gravity of asteroids presents unique challenges. Traditional mining techniques that rely on gravity to hold equipment down or move materials will not work. Specialized anchoring systems and material handling methods are needed. Loose regolith could simply float away. Current technology, while rapidly advancing, is not yet fully capable of the scale required for space mining to be truly profitable. Autonomous robotics. Human intervention in deep space is limited. Therefore, mining operations must be highly autonomous, capable of self-diagnosing problems, adapting to unforeseen conditions, and executing complex tasks without real-time human control. This requires significant advancements in AI, machine learning, and robotics. In space extraction and processing, developing machinery that can extract minerals from an asteroid's surface or interior in microgravity, in a vacuum, and then process and refine them, is incredibly complex. Traditional crushing, grinding, and smelting processes are designed for Earth's gravity and atmosphere. New techniques such as thermal extraction, chemical leaching, or electrostatic separation are being investigated. Transportation and return. Once resources are extracted, how do you get them back to Earth, or to a lunar base, or to an orbital fuel depot? This requires robust, cost-effective transportation systems. Safely and economically returning large quantities of material to Earth's surface is a major hurdle. Technologies like mass drivers, electromagnetic launchers, or asteroid redirection systems are theoretical but far from practical application for high-volume returns. Power systems. Deep space missions require reliable and powerful energy sources. While solar panels are effective closer to the sun, or for operations in shadow, more advanced power systems like compact nuclear fission reactors, kilopower, may be needed. Resource characterization. Developing highly accurate remote sensing and in situ instruments to precisely map an asteroid's composition before a mission begins is crucial for economic viability. Knowing exactly what you'll get before committing billions of dollars to a mission is paramount. 12. Economic viability. Even if the technical challenges are overcome, the economics of space mining remain uncertain. Upfront costs. The initial investment required for space mining missions is enormous, billions of dollars for research, development, launch vehicles, and spacecraft. Recouping this investment requires significant returns. Market disruption. If an M-type asteroid delivers trillions of dollars worth of platinum, it could flood Earth's market, causing platinum prices to plummet and potentially making the entire project unprofitable. This requires careful market analysis and strategies to control supply. Demand and applications. While demand for critical minerals is high, the true economic viability will depend on where these resources are used. If they are primarily for in-space manufacturing and propulsion, the economic model shifts significantly, becoming more about building a space economy than shipping material back to Earth. This is a critical distinction. This final frontier also brings complex legal and ethical questions. Ownership and property rights. Who owns the resources on an asteroid? The 1967 Outer Space Treaty states that no nation can appropriate outer space. However, it does not explicitly forbid private entities from extracting resources. New national laws are emerging, but international consensus is still needed to prevent potential conflicts. This is an evolving area of international law. Environmental concerns. Even though space is vast, there are still environmental considerations. What are the long-term impacts of large-scale asteroid mining on the space environment? Could it create hazardous debris fields? How do we prevent contamination if potentially life-bearing planetary environments are discovered, though unlikely on most target asteroids? Without clear international regulations, there is a risk of a gold rush mentality, where multiple entities rush to extract resources without coordinated oversight, potentially leading to chaos and unsustainable practices. Despite the immense challenges, the drive to mine space resources is powerful, built on a consensus that humanity's long-term prosperity and expansion depend on it. This journey will be incremental, characterized by both bold leaps and cautious, methodical steps, step by step, from water to metals. The first phase of space mining will likely focus on the most immediate, valuable, and accessible resource: water ice. Lunar water ice. Missions to the lunar poles have already demonstrated significant water ice reserves. This will be crucial for establishing lunar bases and serving as a testbed for ISRU technologies. Extracting, purifying, and breaking down water into hydrogen and oxygen on the Moon will be a monumental achievement, paving the way for asteroid-based fuel depots, NEA water. As technologies mature, missions will target the water content of C-type near-Earth asteroids. Establishing a network of orbital fuel depots, resupplied by asteroid-derived water, would revolutionize space travel, making missions to Mars and beyond far more feasible and economical. This would be a true game changer, breaking the tyranny of the rocket equation that dictates the amount of fuel needed to launch fuel. Once water extraction and utilization are proven on a commercial scale, the focus will gradually shift to metallic resources, high-value metals from NEAs. Initially, smaller quantities of high-value platinum group metals from S-type or M-type NEAs might be targeted. These could be returned to Earth for terrestrial markets or used for specialized manufacturing in orbit. The economics here are complex, but the high-value to mass ratio makes them attractive targets. Large-scale main belt mining. The grand vision of tapping into the truly immense wealth of the asteroid belt, like 16 Psyche, is a longer-term prospect, likely decades away. This would require an entirely new level of infrastructure, including large orbital processing facilities, advanced robotic fleets, and even human crewed operations in deep space. To fully realize the potential of space mining, continued breakthroughs in several key areas are essential. Advanced robotics and AI, truly autonomous, self-repairing, and self-optimizing robotic systems will be indispensable. Imagine swarms of intelligent mini-miners working in concert on an asteroid, adapting to changing conditions for months or years without human intervention. In space manufacturing and 3D printing, the ability to print complex structures and components using asteroid-derived metals will be revolutionary. This isn't just about extracting resources, but truly building entire spacecraft or habitats in space, dramatically reducing Earth launch costs. Imagine a fully self-sufficient space economy. Propulsion systems. More efficient and powerful propulsion systems are needed. Ion thrusters are a step forward, but systems like nuclear thermal propulsion or even more exotic designs, capable of both high thrust and high efficiency, will be crucial for the rapid transport of large quantities of material. In space energy generation, reliable, powerful, and scalable energy solutions for long-duration deep space operations are critical. This includes advanced solar panels, potentially solar concentrators for high-temperature processes, and compact fission power systems for distant or shadowed operations. Resource characterization, developing highly accurate remote sensing and in situ instruments to precisely map an asteroid's composition before a mission begins, is crucial for economic viability. Knowing exactly what you'll get before committing billions of dollars to a mission is paramount. Broader impacts. A transformative future. The successful development of space mining could have profound impacts, far beyond simply acquiring more resources. Multi-planetary economy. Space mining is a foundational pillar for establishing a truly multi-planetary civilization. It provides the necessary raw materials and fuel for sustained human presence on the Moon, Mars, and orbital habitats, lessening our reliance on Earth and opening up new frontiers for industry and settlement. Reduced Earth environmental strain. While not a complete solution, a vast supply of space resources could alleviate immense pressure on Earth's ecosystems from terrestrial mining, allowing for environmental restoration and more sustainable practices on our home planet. New industries and job creation. The space mining industry itself, from robotics and AI development to materials science and space logistics, will create entirely new economic sectors and generate countless high-tech job opportunities. Technological spin-offs. As with all grand challenges like space exploration, technologies developed for space mining are bound to have spin-off effects that improve life on Earth, such as advanced robotics for hazardous terrestrial environments, and new materials and energy solutions. Scientific discovery. Asteroid missions undertaken for mining purposes will also yield invaluable scientific data, enhancing our understanding of the early solar system, planetary formation, and even the origins of life itself. Every mission is also a scientific expedition. The vision of space mining is grand, challenging, and undeniably audacious. It is a testament to human ingenuity and our relentless drive to explore, innovate, and prosper. From the gleaming, metal-rich core of 16 Psyche to the icy veins of carbonaceous asteroids, our solar system holds resources that could reshape our future. The Platinum Planet isn't just a fantasy. It's a symbol of the immense wealth and potential that awaits us beyond our atmosphere. This race to unlock the cosmos treasures has already begun, propelled by private companies, supported by national space agencies, and driven by humanity's fundamental needs and aspirations. The challenges are immense: the vastness of space, the harshness of the environment, the complexity of the engineering, and the uncharted waters of space law. But the rewards are even greater: a future abundant in resources, sustainable expansion into the cosmos, and the birth of entirely new industries. This isn't just about wealth. This is humanity's next great leap, an adventure poised to fundamentally transform our economy and even our place in the universe. Are you ready to witness humanity's greatest gold rush? A true rush to the stars?